So I've illustrated that if a matrix is in echelon form, its non-zero rows form a basis for its row space. How can we use this idea when our matrix doesn't happen to be in echelon form? What we want to do is transform it into a matrix that is in echelon form, that has no zero rows, and such that the row space is the same as the row space of the original matrix. So in this, we'll represent our current matrix as a row list rather than using the mat class. So let's assume the variable row list has been initialized with a list of vecs, such as this one. Our code will mutate this variable. To handle vecs with arbitrary domain D, we have to decide on ordering of the columns. So we'll use the sorted order as shown here. So the goal is to transform a matrix into one in echelon form. And our first approach will be using sorting. So the algorithm will first choose a row with a non-zero in the first column, then choose a row with a non-zero in the second column, and so on. And it'll accumulate these rows in a list, new row list. In order to carry this out, the algorithm has to keep track of which rows are remaining to be sorted. It uses rows left to store the set of indices of rows that haven't been processed yet. So the initialization we've already discussed. Here's the code for the algorithm proper. The algorithm iterates through the columns, and in each iteration, it finds the set of row indices among those rows still remaining to be sorted that have a non-zero entry in the current column. It selects one of those rows, in this case the first in the list, adds that to new row list, and removes the index from the set rows left of rows yet to be processed. Let's see how this algorithm operates on a matrix. So the algorithm iterates through the columns one by one. First, it considers the first column. It finds a row with a non-zero in that column. So this row. And adds that to new row list. Goes to the second column, finds a row with a non-zero in that column, and adds that to new row list. Now, the algorithm runs into trouble. When it gets to the third column, it doesn't find any rows that have non-zeros in that column. So rows with non-zeros will end up being empty, and this line will cause an error. Now what the algorithm should really do is just move on at this point to the next column. So since column 3 doesn't have any non-zeros among the remaining rows, it moves on to column 4, and it finds this row, adds that to new row list, and finally goes to the next column and finds this row and adds that to new row list. So we should change the code to handle this case. So we add a check to make sure that there are some rows with non-zero elements. If not, the algorithm just moves on to the next column. The algorithm's still not correct. Let's see how it works on this matrix. It'll produce this matrix, which unfortunately is not an echelon form. We don't have this nice staircase going down because it, whoops, this is non-zero. So we're going to need to make a change to the algorithm. The algorithm is actually going to have to change the vectors. Let's consider the algorithm at the point where it's eliminated these rows. It's dealt with the first, second, and third columns, and it's ready to deal with the fourth column. At this point, it has to apply a transformation. It has to change the rows. What it does is it subtracts twice this second row from the fourth row, getting this. This has the effect of zeroing out this element. So here's the result. And this 3 is called the pivot element. That's what we used to zero out this element. The transformation we performed is equivalent to multiplication by an elementary row addition matrix. And such a matrix is invertible. In fact, these matrices are inverses of each other. We'll show that if M times A equals B, where M is an invertible matrix, then the row space of A equals the row space of B. That means that this change to the rows that the algorithm performed doesn't change the row space. Therefore, a basis for the row space of the changed matrix is also a basis for the row space of the original matrix. We'll first prove this lemma. Given matrices n and A, the row space of n times A is a subset of the row space of A. Let V be any vector in the row space of n times A. That is, V is a linear combination of the rows of n times A. Well, we can write it like this. V equals some vector times n times A. Using associativity, we can rewrite this as U times the matrix n all times A. And now this is a vector times a matrix. So this shows that this vector is a product of a vector times the matrix A. So by the linear combinations rule of vector matrix multiplication, this is a linear combination of the rows of A. We've shown that any linear combination of the rows of NA can be written as a linear combination of the rows of A. And that completes the proof. So we have this lemma. Now let's go back to the proposition. If M is invertible, then the row space of M times A equals the row space of A. To prove that, we prove two directions. We prove that the row space of M times A is a subset of the row space of A, and vice versa. First, let's show that the row space of M times A is a subset of the row space of A. Well, that's a direct application of the lemma. To get the other direction, we define the matrix B to be M times A. Now, M is invertible, so it has an inverse, M inverse. Multiplying this equation by M inverse, we get this. M inverse times B equals A. Now an application of the lemma shows that the row space of M inverse times B is a subset of the row space of B. Well, this is just A, and this is just M times A. So what we've really shown is that the row space of A is a subset of the row space of M times A. And that was the other direction. So that completes the proof of the proposition. So applying elementary row addition operations doesn't change the row space. Let's incorporate this new feature into our algorithm. You notice I've added this line in which we add suitable multiples of the row indicated by the pivot index to each of the rows that has a non-zero in the current column. So applied to this matrix, for example, after some iterations of the algorithm, this matrix turns into this matrix. Now the algorithm subtracts multiples of this row from the other two remaining rows. So this is the pivot element in this case. And here's the result. We've zeroed out this column. It also happens to have zeroed out these other elements as well. So here's the new code. The algorithm iterates through all the rows with a non-zero in the current column, other than the one we selected as the pivot row, and then subtracts an appropriate multiple of the pivot row from each of those rows. Now, this algorithm is mathematically correct. However, we have to cope with the fact that our computer computes not with real numbers, but with floating point numbers. Let's say we started with this matrix. We want to compute a basis for the row space of the matrix. One iteration of our algorithm will produce this matrix. And notice this 1 minus 10 to the 20. What does Python do with an expression like that? Let's find out. The result is just negative 10 to the 20. Because of rounding error, therefore, the matrix that really results is this one. where we've replaced 1 minus 10 to the 20 with just minus 10 to the 20. One additional step, the algorithm, results in this matrix, which leads us to think that the first two rows of this matrix form a basis for the row space of the original matrix. But in fact, the row space of the original matrix has dimension 3. So we've been misled. The problem is Gaussian elimination got the wrong answer due to round off. Now, all of our algorithms are subject to such errors. There is a way to help Gaussian elimination get the right answer. According to partial pivoting, the algorithm should select among the rows remaining whichever row has the element of largest magnitude in the current column. Complete pivoting means that the order of columns can't be decided in advance, and that the algorithm should search among all remaining rows and columns to find the entry with largest magnitude. Now, these are a bit complicated to implement. We won't study them. Instead, we'll see how Gaussian elimination is used when the matrices are over GF2, in which case we don't have any rounding errors to worry about. Let's see how the algorithm operates on a matrix over GF2. The algorithm starts with column A. The algorithm selects row 1 as the pivot row, so it puts that row into new row list. And now, since rows 2 and 3 have non-zeros in column A, the algorithm uses the pivot row to wipe out those non-zeros. And here's the result. Now, column B. The algorithm selects row 3 as the pivot row, adds it to new row list. The other rows have zeros in column B, so we don't have to do any row addition operations. Let's move on to column C. The algorithm selects row 0 as the pivot row, adds it to new row list. And then there's only one row remaining that has a non-zero in column C, so the algorithm adds the pivot row to row 2 to make that 0. Finally, column D. The only remaining row is row 2. So the algorithm selects row 2 and adds it to new row list. And no other row operations are required. The algorithm is done, and it's come up with a basis for the row space. So far, we've seen how to use Gaussian elimination to transform a matrix into one in echelon form. And we know that the non-zero rows form a basis for the row space of the original matrix. But there are other things we can do with Gaussian elimination as well. We can use it to solve linear systems, and you'll see that can be useful, for example, in lights out. We can also use it to find vectors in the null space of a matrix, and that can be useful, for example, in integer factoring. The key idea is to keep track of the transformations that the algorithm performs in putting the matrix into echelon form.